So we're going to move on to chapter 2, which is still somewhat of a math review with one concept that is truly chemistry, and that is the idea of density. But we're going to start by just making sure that everybody's okay with scientific notation. Any questions about that? So we have psi notation, check. We have more or less sig figs, significant, digits. Any questions about that? Feeling okay? Conversion factors, we're going to keep using them, so we'll get back to that today. So conversion factors and units. So we're going to continue to work in the metric system, in the SI, leaving behind any references to the English system. Of course, we are going to be using that on occasion. And then also percentage. We'll be talking about percentage today again in the context of density. But that's essentially what we have covered. And what is coming up is going to be mostly a combination of all of these things in addition to this idea of density. Okay, so let me just remind you that in chemistry we study matter, and there are properties of matter that are measurable. So we measure properties of matter that can be either the length of a sample, it can be the volume of a sample, can be the mass, the weight, if you will, of a sample of matter, and then the temperature. Those properties that I just mentioned are somewhat variable between different samples. I mean, I shouldn't say somewhat, very variable. They change with the size of the sample, with the nature of the sample, et cetera, et cetera. But there are properties of matter that are more uniquely attached to certain types of material. So for instance, density, the one that we're going to explore today, is actually something that can describe the nature of the sample that you are dealing with. So it's almost like your fingerprint. You know, your fingerprint is only your fingerprint and nobody else's. Or maybe even the Social Security number in the US. That's an identifiable piece of information that belongs to only you. Well, the mass of the table doesn't belong to the table because I can weigh something else that weighs exactly the same thing, the same weight as this table. So I can have this on a scale and say is 40 kilograms, but I can put some, cat on it that would be a very heavy cat. 40 kilograms is about 80 pounds. Okay, I don't know, better example than that, maybe a horse. That may be a light horse, but you get the point, okay? So 40 kilograms of something else will be something else, completely unrelated. However, the density of the table would be unique to the table, and it would be different from the density of that imaginary heavy cat, okay? Now, let's define it once again. I mentioned it to you last week at the end of the lecture on Thursday. So we're going to define density as a ratio. It's a proportion, if you will. And the proportion is related to the mass of the object or the sample, the material, divided by the volume of that same sample. So you cannot take the mass of something and then use a different volume for that something. It has to be the same sample size. Now, we're going to measure in chemistry primarily the mass in grams, which is the SI unit, and the volume in milliliters, which actually is 1,000 of the actual liter volume SI unit. But that's the way it was defined, and that's the way we're going to use it. Now, for the purposes of this course, let me remind you that 1 milliliter is almost always the same as 1 cubic centimeter, which is also known as a cc. Cubic comes from these 3. So when you multiply 2 numbers by each other, you have a square, the second power. When you multiply the same number 3 times, you have a cubic measurement. And that's where that 3 comes from. So it's a cubic centimeter. And again, for the purposes of this course, we're going to consider these two the same, these two the same. So sometimes you may see grams per cubic centimeter. Okay? Now, with that information, we can actually see that you have some sort of a simple mathematical formula. To make things a little bit easier, I'm going to use symbols, and I'm just going to use common symbols. So a capital D for density, lowercase m for mass, and somewhat of a lowercase v for volume. This is the same thing abbreviated. Now, sometimes you actually know the density of a material. You may measure the volume of that material, but you may not know the mass, and you want to find that out. Well, we can manipulate this equation using algebra to set up 2 other equations that are equivalent. So we can set up these in terms of mass. So the mass of a sample is related to the density of that sample and the volume of that sample by reorganizing these, and now we have D times V. Sometimes I use the little x as the times symbol. Sometimes I use a dot. Sometimes we use parentheses. So this is the same as that and as that. So please get used to the fact that I may switch from one way of writing it to a different way of writing it. Now we can also imagine a scenario where you know the mass of a substance, of a sample, you know the density of that sample, but you want to find out the volume. So for that, we would have a third version of this formula in which we would relate the mass to the density as such. Okay? Now, of course, there's no need to memorize these 3 formulas. Let me put them in rectangles here. That's one, that's the original one. That's one version using mass as the unknown. And then this is the third version using volume as the unknown. Those 3 we're going to be using, and you're going to have to determine by looking at the data, the numbers that you get on the problem, the type of problem, which of the 3 you need. Needless to say, it would be a lot easier if you just remember one formula and you are able, because you remember a little bit of algebra, to reorganize it. But if that becomes, you know, an obstacle, just write the 3 formulas down from the onset and have them ready, available to you. Not a big deal, okay? Now, the units, if you look at these, and let's look at that dimensional analysis, would be for density, grams over milliliter. For mass, let's check this out. So if we have mass, and we put the units of density and the units of volume in the formula instead of the T times V, we're going to have grams per ml multiplied by the units of volume, which are typically milliliters. So you can see here that using dimensional analysis, the units themselves as mathematical objects, we can cancel out milliliters. This milliliter is on top of a fraction, which we don't write. but it's typically seen like that. That cancels with that, and the mass is in grams. So we know that this formula is right because it gives us mass in grams. Let's check this formula to see if it's right. Volume should be milliliters. So let's see if the dimensional analysis gives us that. So we're going to put volume equals the units of mass on top divided by the units of density on the bottom. This one is a little tricky because when you look at that, it's like, okay, so what do I have here? I have grams divided by milliliters. Well, yes and no. If you remember, these units come from this D, which is a single measurement. So we really have these. We have grams divided by 1. It's a fraction, just as it was for this other one over here. And then we do have the grams divided by milliliters. If you remember your fraction rules, that means that these grams and these grams cancel each other out. That also means that these milliliters, which is at the bottom of the bottom, ends up moving to the top. I'm not an algebra, I'm not a fractions teacher, professor, whatever, so just trust me when I tell you that. So this essentially results in that. I know it can look confusing, but you don't have to be doing this unless you're checking yourselves as to whether or not you're using the correct formula. If you have these 3 formulas, now we know that they are the correct formulas, so don't agonize over having to do this dimensional analysis. It's doable, but it may not be something that you want to do or that you have the patience to relearn. So just let your trust on these 3 formulas guide you. Okay? Yes? What are the units for density? Over here, grams per milliliter, always. I mean, they can be any mass divided by any volume. So the units of density could be kilograms per liter. That's correct, but it's not what we typically use. Or they could be even ounces per fluid ounces. That's weird. We'll never use that in chemistry. But that would be density units. Any units of mass divided by volume would be the correct units. The ones that we're going to use most of the time are grams per milliliter or grams per cubic centimeter, because they're the same. Assignments. Let me reopen the homework. There's several clicks, unfortunately, that you had to do before you get to the place. Okay. So let's make this a little bit bigger. Is that good enough? Everybody can read that? I can try one more Zoom. I just don't want to miss. Is that better? Okay. So all of these homework questions, just as the quizzes, are going to have several titles. So, bless you. So there is the first attempt to chapter 2 homework, the name of the question, and then the parts of the question. Remember, you have multiple attempts to each question, and then you also have multiple attempts to each homework. So there should be ample opportunity for you to really learn the material. Not just to try without thinking. You need to be thinking, you guys. It's for your own good. So match the type of measurements to the unit given below. Match the word in the left column to the appropriate blanks in the sentences on the right, etc., etc. Make certain each sentence is complete before submitting your answers. So what do we need to do? We need to drag these things somewhere in here, drop them, and make sure that they are in agreement. Now, if you're doing this with me, if you brought your phone or your laptop or your tablet, the question may be a little different. So they get scrambled, but the idea is the same. Now, Milliliter. That's what type of measurement? Volume. So we're going to drag volume there. Now that is an abbreviation, and it's an abbreviation for this, not the milliliter, but the millimeter. So what would that be measuring? Meter is actually distance. So meter measures length. Okay? What about gram? Easy, right? Mass. 125 K. I mentioned way back when the Kelvin unit. So is that temperature? Yes. And finally, kilometer. So the part meter or kilometer tells us that is distance, right? Okay, so let's just drag them very quickly. Make sure that we did it right. As you can see, oh, there's no density here. Volume and mass. I guess we can use the same multiple times. If you're using the homework to study instead of to provide you with feedback, feel free to request answers even before you attempt. I mean, this can be a learning tool. It doesn't have to be punitive. It doesn't have to be grading you, because you have ample opportunity to get 100. So use the attempts as you wish. Okay? So I'm going to submit it, and the feedback should come back immediately. When the answer is correct, sometimes you get an explanation. Sometimes if it's just straightforward, you don't get any explanation. Okay, so that was part A. Is there supposed to be a part B, or that's it for that question? Looks like this question has only one part. So let's move on to the next one. This has a very brief explanation. In fact, there's no description of the question. There is the title of the problem, and straightforward. 5.21 centimeters is the same distance as. Now, this one is a tricky one because you have to make sure that you do this problem several times. Asking AI, asking ChatGPT this question is a little tricky. You can give ChatGPT all of the options, and it will probably help you. I haven't tried it. So let me tell you let me use a word here. See if it makes any sense to you. I'm going to use the approach known as brute force. Anybody knows what that means? Brute force.
Oh, brute force?
What does it mean?
Yeah, like aggressive.
Like the hard way.
Yeah.
Aggressive, yes. So I'm gonna do this problem the hard way, meaning I need to convert this unit to each of these units and see which one is the right answer. So the good news is that these two are both meters, so we're gonna eliminate that in one shot. But let's start by writing, okay, so we have 5.2 centimeters, 5.21 centimeters. I wanna convert that to meters first. Well, what do I need for a conversion? I need a conversion factor. So I need to remember or look it up that 1 meter equals 100 centimeters. That's what I need to make this conversion. Now, also keep in mind that I told you last week that from every equality you get two conversion factors. You get one in which the meters are on the top of the fraction, and another one where they are going to be on the bottom. So these two are my conversion factors, and I need to choose one to put in front of this and multiply that number by that so that I get the meters answer. So times. I want to get meters, so I want meters on the top. I want to cancel centimeters, so I want centimeters on the bottom. So I'm going to choose this one right here. 1 meter divided by 100 centimeters is my conversion factor. And if I carry that operation in my calculator or ask the computer to do it for me, I end up with 0.0521 meters. That's the answer.
So
Yes?
you multiply 5.21.
So I multiply 5.21 by 1, and then I divide it by 100. Okay?
Thank you.
You're welcome. So that's how I got this number without my calculator. Looks like that and that are the same, right? The top answer and this answer are the same. So let's keep moving. I'm not saying that that's the only possibility. I mean, this is going to give us a lot of practice with conversion factors. So here we go. I have converted centimeters to meters. So now I need to convert centimeters to kilometers to make sure that this is not the right answer. Okay, so I need to convert centimeters to kilometers. For that, I need a new conversion factor. I'm going to erase all of this stuff. And once again, we're going the hard way. So I'm going to show you the hard way, and then if you happen to think there's a much easier way, that's up to you, but I have to show you every step of the way. So there's no conversion factor for centimeters to kilometers that I know about, so I have to come up with it. So I do know that 1 meter equals 100 centimeters. I had that on the board, right? I erased it. The prefix kilo means 1,000. So I also know, and this is, of course, because I'm the professor, but because I'm pretending to be learning this again, if I look at my notes or at the book, I know kilo means 1,000. So it basically means that 1,000 meters are 1 kilometer or kilometer. But I don't have a relationship of kilometers or kilometers to centimeters. So unfortunately, I had to somehow create it from here. Okay? I want to keep centimeters and I want to keep meters. So if 1 kilometer contains 1,000 meters and 1 meter contains 100 centimeters, I think I can rationalize that that times that is going to give me the right equality. Right? The centimeter is smaller than the meter. The meter is smaller than the kilometer. So multiplying the two numbers, 1,000 times 100 is going to give me a number with 5 zeros. Oops. And that will tell me that 1 kilometer equals 100,000 centimeters. You can do that actually using these two conversion factors and getting rid of meters, eliminating meters. So let me show you how do you do that. You have 100 centimeters divided by 1 meter, right? That comes from that equality. Agree? Everybody knows that 2 come from that one that I chose to put there. I want to get rid of meters, so I'm going to make another equality, a conversion factor. This time I'm going to put meters on the top so that I have kilometers still at the end of my dimensional analysis. Meters and meters cancel each other out, so 100 centimeters times 1,000 without units gives me 1 kilometer. If I do the operation, I end up with this. Which if I work backwards now, that's my equality. Right? If I go backwards from using equalities to get conversion factors, now I have a conversion factor, I want to make an equality. I'm saying 1 kilometer equals 100,000 centimeters. Same thing. So I ended up with that, which I predicted was that. That's why this is the hard way, isn't it? I mean, don't get me wrong, you can be actually Googling this stuff, but you now know how it actually works. So we're going to use this conversion factor to turn centimeters into kilometers. I want kilometers at the end to be left with me, so I'm going to put kilometers on the top. 1 kilometer or kilometer divided by 100,000 centimeters. Centimeters cancel each other out. That divided by that gives me, well, 5 zeros. 0.0000521 kilometers. 2, 3, 4, 5. Is that what is in there? 0.000.0000. So that's not the answer. It's a little tricky, right? Because it almost looks like the answer. But it's different by 1 0. So that one is out. Apparently that one is out too. So we have 2 more to do. We're now in decimeters. Okay? We need to prove, we need to make sure that this is not the same as that number. That's what we need to make sure, because otherwise that would be also a possible answer. So I'm going to ask Wolfram Alpha, how many decimeters are in 5.21 centimeters? That's going to be my question to Wolfram Alpha. So let's do it. Or even to Google. How many, and I'm going to spell it out, decimeters are in, what is it, 5.21 centimeters. And it should make the conversion for us. So convert 5.2 centimeters to decimeters is 0.521 dm. Let's keep that number in mind. 0.521. What is the choice in the homework? 52.1. The numbers are different. So this is wrong. That number and that number are not the same. This number and 0.521 are the same. So we have eliminated another answer. Now we have the millimeters. Same thing. We can either do it with numbers, and I'll do it both ways just to finalize this idea, or I'm going to ask how many millimeters are in 5.21 centimeters. So now we're going to change that to millimeters. And the answer is 52.1 millimeters. Oh my goodness, is that the same? I mean, was that there? Let's take a look. 52.1 millimeters. Oh no, thank goodness. 5.21 millimeters. I thought, my God, we're going to have 2 right answers. 5.21 millimeters. So that's wrong as per Wolfram Alpha. If we do it by hand, I'm going to do it in a slightly different way. Now, and I'm sorry for assuming, but with practice, this becomes second nature, and then you're going to be talking like me, saying, well, as you know, or as you should know, and I don't mean to be patronizing by saying that, but let me rewrite something here. 100 centimeters are 1 meter, right? By now, everybody should remember that. Don't be ashamed if you don't, but I have said it several times. Now, this is also true. 1,000 millimeters are equal to 1 meter. So milli means 1,000. In this case, dividing by 1,000, the meter. So from these 2 relationships, I hope you can see that the centimeter is bigger than the millimeter, right? In fact, it's how many times bigger? If I divide 10,000 by 100, I find the answer is 10 times bigger. So 1 centimeter is 10 times bigger than 1 millimeter. What I'm saying is that 1 centimeter equals 10 millimeters. Now, if you don't believe me, look at a ruler. The ruler is divided into centimeters. So from 0 to 1, from 1 to 2, and then each centimeter has 9 lines. 1, 2, 3, 4, 5, 6, 7, 8, 9. So each division is 1/10 of the centimeter, so it's a total of 10 lines between 1 centimeter and 1 centimeter. Does that make sense? Okay, so we know that that answer is wrong. We know that one is wrong. We know those two are wrong, and the first one was the only one that was correct. Nasty, simple-looking problem, right? I mean, this is time-consuming. But once again, use the technology. If you were treating a patient in some hospital and you wanted to do everything by memory instead of using the computer that you have there, that patient would be really sick or dying or maybe dead if you didn't act quickly. So you had to rely on technology. And to me, that's perfectly acceptable. Okay? Now, when you do this problem at home, if you're not doing it right now here with me, remember that the numbers are going to be slightly different. But now you have a better idea as to how we approach this. It looks cumbersome, no question about it. Okay, I'm going to skip the ones that are just memorization because you can look this up in your book. Same thing as the previous problem, except that there's a little bit more information here because they're giving you the 2 units instead of giving you multiple units here. I mean, can you imagine if these had centimeters, decimeters, millimeters? That would be like the other problem. So let's do this one just to make sure that we know conversion factors in every possible way. The problem is telling us to convert how many centimeters to inches. How many centimeters are in 57 inches, okay? So always start with writing the information that you have, 57.0 inches. We're going to have to convert that to centimeters, so we need a conversion factor that is going to give us centimeters. You guys gave me a conversion factor for this problem before. I remember that last week. You told me that 2.54 centimeters are 1 inch. If I remember correctly. I think I wanted to go with 2.56, but you corrected me and it was 2.54. So this is what we need to come up with a conversion factor that is going to go there, that when multiplied to this known amount is going to give me centimeters. So I want centimeters on the top, I want inches on the bottom, because that will cancel out the inches. So 2.54 centimeters divided by 1 inch. That comes from here. And now if we do the math, we're multiplying 57.0 times 2.54, and we're dividing by 1. Let's do it with Wolfram Alpha and then with Google, just so that you see you have the same. How many centimeters are in 57.0 inches? 57.0 inches. And with Wolfram Alpha, you probably want to spell out the units just to make sure that it's understanding what you are doing. This is so small, I'm sorry. So the language that Wolfram Alpha is using is convert 57 inches to centimeters. Notice that he got rid of that, and that's significant. So you guys are going to have to still be thinking, because we're going to have to choose the right number of significant digits. So here's the answer. 144.8 centimeters. $144.8. Now, before we look at the choices, remember, for significant digits, conversion factors don't count because they are infinite. What counts is the number that you got for the problem. So how many sig figs are in 57.0? 3. The 0 counts because it was added there. It's not a placeholder. It was added there as a measured part of the number. How do I know that? Because it's different from writing that, which is what Wolfram Alpha is saying. That has only 2 significant digits. Okay? So how do we write 144.8 with 3 significant digits? How do we round that up? So this 8 tells me that I have to drop it, and this has to increase by 1, so it's 145. I can put the period, but nothing after that. Or I cannot put the period, and the 3 numbers will be significant. So those 2 answers are the same. What were the choices? I forgot by now. Okay, so they're not trying to trick us. This is not a tricky question. In other words, what would have happened if I had a 144.8 choice? I would have had to pick this one, not the 144.8. Understood? Okay, so we are going to choose 145 centimeters and submit it. Any questions about that problem? So we're still somewhat reviewing what we did last week, which is perfectly fine. Okay, let's move on, and I do want to have time to look at density. So let me just move. This one I think is something that you can play with. They are tables with these prefixes in them that you can actually consult. So there's no explanation there. Same thing here. This is describing different types of measurements in the basic ways that we have done it before. Okay, no problem there. Oh, this one, let's take a look, because this one is going to emphasize and reinforce the idea of counting versus measuring. Okay? Bless you. So we need to label these different statements as whether the measurement is whether the number is an exact number or a measured number. Now, I already started with the first one sort of hesitating. I'm sorry, but I'll tell you why. Let's jump to the second one. A lab test showed a blood sugar level is 350 milligrams per DL. If you tested something, you had to measure it, right? You didn't. It's not an exact number. It could have been measured by somebody as 351. It could have been measured by somebody as 349. Now, if it comes from a readout, from a digital display, it's still a measured number. Because if you look at a scale display, if you have a balance in the lab, I can show you that on Thursday, and you put a sample, it's going to tell you 350, and then 351, and then 349, because there's wind or air coming. So it's a measured number. Anything that you test, think about it in terms of counting. If you count, then it's an exact number. If it's a conversion factor, it's an exact number. So that's why I hesitated with the first one. Let's go to the third one. There are 452 pages in a book. You counted those pages, right? So those should be exact. You really cannot have 452.1 pages, right? Or 450 pages, 0.0. You have 452 or 453, but you count them to come up with the, so we're gonna go with exact, measured. The rabbit weighs 2.5 pounds. So once again, the scale. So measured. There are 100 aspirin in a bottle. That's a tricky one. Because you can actually cut an aspirin in half, right? So you could argue that you have 100.5 aspirins. Well, it's a trick question. Of course, it's counted. You counted the pills as wholes, not as half pills. So we're gonna have to go with our instinct and say exact. You feel ill and your temperature is 100.1, so you measured it, right? Now this one, I'm gonna go with exact simply because it's an equivalent, conversion factor. 1 mile equals that many feet. Even though I don't see a point there or more zeros, that's what's gonna be my guess. And if I'm wrong, I'm gonna get feedback. Any questions? I'm gonna submit it. Oh, I'm gonna get 1 or 2 wrong. Oh no, we did them all right. I really wanna go to density, and we have only 20 minutes left. Those are significant digits. Please do it and make sure you learn from it. This is still homework 2. It'll be open all the way until next Sunday. I mean, this coming Sunday. Same thing, significant digits. Significant digits. This is a longer homework. I'm trying to find density problems. I'll be happy to go back to these problems on Thursday, you guys, once we finish with density. But I'm skipping them from now because I really do want to give you a heads up on how to handle density problems. Okay. This is a percentage. So on Thursday, if I don't have time today, I want to do this problem with you guys. Right now, let me keep pushing to find density. Are there going to be any density problems? Huh. Not yet. Here we go. Finally. And actually, I'm glad we're looking at this problem because it's going to give me a chance to describe to you something that later in a virtual lab, which I can actually demonstrate in the physical lab to you, we're going to be doing the measurement of volume by displacement. So let's take a look at this question after I'll give you an imaginary experiment. So I'm going to put 2 cartoons here for you to consider. And I'm going to just use these imaginary numbers. So this is going to be 60, this is going to be 75 to that line. Both of them are milliliters. So let's look at the first cylinder. So this is a cylinder with water and the volume of water is 60 milliliters. Okay? Now, taking this same cylinder, I'm going to drop a marker. You know, this marker. I'm going to put it right here at the bottom. Boom. It drops to the bottom. So I have my marker. I don't know. Looks like that. And the volume goes up to 75 after I drop the marker. I started with 60. I added the marker. It went up to 75. What is that telling me? Indirectly, or maybe directly. Why is the water going up? Because the marker has a volume. And it has a volume equivalent to the volume displaced. The volume that was pushed up is the volume of this marker. If I wanted to use geometry to measure this thing, that would be really complicated. It's a cylinder. It's not even a perfect cylinder. So I would have to know the formula for the volume of a cylinder, measure the diameter, calculate the radius, the height. Too complicated. So this method by displacement gives you the answer immediately. So the volume of this marker is the difference between those two numbers. Understood? So in this problem, we have a similar situation. They tell you that you have a gold nugget with that mass. So we have 521 grams in a gold nugget. So gold. Chemical symbol AU from the periodic table. Information from the problem. The mass is equal to, I forgot, 521 grams. And then it says, that nugget is added to 50 mLs of water. So we have our cylinder with 50 mLs. You add it. The volume goes up to 77. And here is a gold nugget at the bottom. So what can we conclude? These are milliliters. About the volume of the nugget. Because the question is, what is the density of the gold nugget? Well, what do we need to have to calculate density? Here's the formula. We need the mass of the sample. We need the volume of the sample. We have the mass. We need the volume. So this is the mass of gold, the volume of gold. What would be the volume of gold? 27. The difference between the 77 and the 50 is 27 milliliters. And that is in fact correct. Now, I'm being sloppy here because the problem tells you that this is 50.0 and this is 77.0. That matters because there are 3 significant units in both measured numbers. This is measured, this is measured. 3 sig figs, 3 sig figs. So my volume is 27.0. To answer the question, I look at the formulas that relate density to mass and volume, and I decide this is the one that is going to give me the answer. So I'm going to put density equals the mass, 521 grams, divided by the volume, 27.0 milliliters. These are both the gold nugget. And now I'll do the arithmetic. Using Google, I can divide 521 without anything else. 521, I'm going to put that line as a dividing and 27.0 as my, I don't even need a calculator anymore sometimes. So it popped up a calculator with the answer, 19.2996, blah, blah, blah. Well, we need to fix that. we need to report these to 3 sig figs. What would you say I should write? I hear 19.3 across the class. And then the units, grams per milliliter.
I was drilled always with the units. I'm afraid whenever I see a number.
Oh, absolutely. You have to. Unless there's very few dimensionless numbers in chemistry. Specific gravity is one. You don't have to say units when you measure specific gravity. But whenever you say something in chemistry that was measured, you need to attach units to it. So thank you for doing that. 19.3 grams per milliliter is going to be our answer. There is a choice there, 19.3 grams per milliliter. Now let me get the wrong answer this time. So I'm going to go with that one. As a matter of fact, let me choose this one and see if that was a trick in which they were flipped. It's possible. We'll check it in a second. So submit. Oh, there's no feedback. So too bad. I was hoping that they would tell you or give you an explanation. No explanation. We're doing that here. So let's try it again. 19.3. And it's correct. Now, before I leave this question, let me see what happens if I divide 27 by 521. So I'm flipping the numbers on purpose. 0.0518. Oh my God, isn't that nasty? So if you flip the numbers and you just run with it and say, oh yeah, great, that backwards, you're going to be tricked. Not my fault, but actually I like it. This is not playing games. This is just making sure that you're doing the right thing. Okay, questions about that? I mean, we'll do more on Thursday to cover all of the other problems that we saw here. Oh, because then it's going to get a little bit more complicated when we introduce ideas that we haven't discussed and that the book touches on very so lightly. So let me, in the next 5 or so minutes, tell you about other ways in which measurements are sometimes conducted that are not length, volume, mass, but more like percentage. So this little symbol of percent really means per 100. In other words, I could actually come up with something that is not normally seen, but I could say parts per 100, pph, parts per 100. Why am I doing that? Well, because here we have something called ppv in this problem with no explanation of what that is. Well, that acronym stands for parts per billion. Now, here's a problem. If you have a friend visiting from Europe or from South America or from even China, and you ask them to write a billion on a piece of paper or here on the board, if I were in Mexico and I was asked to write a billion, this is what I would write. Why? Isn't a billion a billion? Sadly, it's not. in the US, a billion is 1,000 million. 9 zeros. This is a billion here. And that's what we have to work with. In other parts of the world, a billion, and you probably know that bi means double, is a million million. That's why it makes more sense. 1 million million, a billion. 1 million million million, a trillion, or trillion, if you will. I think this in the US is a trillion. But we are in the US, so that's what this means per 1 per 100 million. Oops. I have one, right? 1,000 million. I said 100, I meant 1,000 million. Okay, so this problem is going to take us a while. I think I'm going to run out of time. But he's talking about a herbicide, and for some reason, environmental scientists use parts per billion, was measured at 3 parts per billion. What does that mean? Well, the amount of herbicide in that sample measured was 3 parts of herbicide in 1 billion parts of soil. So 3 parts of herbicide in 1 billion parts of soil. That's what 3 ppb means. So then the question is, how many micrograms of herbicide are present in 1 pound of soil? Yikes, that looks weird. Well, it's 1 pound of soil, not 1 kilogram of soil, not 1 microgram of soil. They're in different units. So we need to rewrite this question ourselves, first converting these to micrograms, so that then we can say how many micrograms of the herbicide are in this 1 pound of soil. I mean, here we have it in a billion, but not in grams or in micrograms or in pounds. So I don't want to rush through the answers, so let's leave this for the beginning of Thursday, and we'll finish this problem on Thursday. If you want to give it a shot, by all means, do. Let me just see what else. We have 2 problems left on the homework that I haven't looked at. So this one has to do with density. I think we can also work on this on Thursday. And then this one also has probably to do with, oh my God, this problem is a nightmare. I remember solving this one. In fact, I have a whole video that I made only on this problem a couple of years ago. It's a scary problem. I'm going to see if I can find the video, and next week I'll show it to you where it is, and I'll send you a link to it. Because I don't think, you know, you can watch that on your own and understand the problem. It's a lengthy problem. Any questions, anyone? Okay, so Thursday I'll see you here for both. We're going to do the lab number 2, the pump. If you have done it already, great for you. It's not the most intuitive of labs, so I hope to be able to help you on Thursday.